Good morning, everyone. My name is Steve Bornkamp. I'm the president of the Romania Green Building Council. Thank you very much for joining us today. Before I make my opening comments, I wanted to introduce a gentleman who is not only the best hotelier in Romania and with a deep commitment to the country, but is also a strong supporter of the foundation of the Romania Green Building Council and a leader in implementing green initiatives into this hotel. Mr. Kurt Strohmeyer, I'd like to ask you to make just a few brief comments. Thanks.
Thank you very much, Stephen. Great introduction. It's great to be with you. As you see, we have also green carpets even here in this room and green chairs. For us as a company, as JW Marriott, we are, as you know, we're an American company established here in Romania since the year 2000. And this is the first luxury brand of Marriott, JW, which has been established in Europe. This is also a very unique situation for us. Also, the Green Building Council, which has been established under the leadership of Stephen, I think it's an absolute great initiative. And this is something where Romania goes maybe a little bit stronger forward than other Eastern or some Western European countries. This is something what we highly endorse and highly support. And it's great to see on those events people like you around which are interested to help ensure to keep Romania, make it more green, and preserve the nature and the environment for our future and for the future of our kids and the kids of our kids. Wish you a great meeting, and it's great to be with you. Thank you.
So I wanted to start today just briefly with explaining why the Romania Green Building Council thinks this is an important initiative. Also give you some hints onto some recently added training events and new events, as well as explain a little details on how you can be involved. One of the things I would remove the maybe from Mr. Strohmeyer's suggestion that Romania could be the top position. It's actually, I'd say, the strongest Green Building Council in setting the direction for the Central East European region. And this is something I'll talk about my optimism for Romania, but I think we've definitely set the tone for the Central East European region. First, we see a continued and growing interest in green construction and environmental responsibility from everyone we meet. In areas of business, government, and society, there's a positive sign. And I have said and will say again that Romania will be a success story and a leader for the region for sooner than we think. There's also a growing demand for investors and for tenants asking for voluntary green certifications in Romania. The European Parliament is right now considering strengthening the Energy Performance for Buildings Directive that is already in force in Romania today. And the buildings you build will require a certificate of its energy efficiency rating. And if you're building a public building, your grade will be posted on the building for everyone to see. There's also better technology and materials that is either increasing in efficiency or coming down in price, and a rediscovery of historical methods of constructing and operating buildings with little or no energy. We have new information technology solutions, some being developed specifically for Romania, that can help you design, construct, and operate the next generation of high-performance green buildings. And as we face an economic crisis, there is considerable economic opportunity. The estimate of the International Energy Agency is that it will require 34 trillion euros of investment to convert our planet to green energy. And that's trillion with a T, not billion with a B. And the building industry itself is a 4 trillion euro industry worldwide. And if you consider that for every euro someone has to invest is a euro waiting for you to be earned, this is a business opportunity for everyone for many years to come. And we have created a series of low-cost training events, workshops, and awareness campaigns to be presented over the next 6 months. And these include, you've heard from Mr. Strohmeyer, but we will be doing next month a Greening Our Hotels on the 20th of February. And he will present some of the JW Marriott Grand's initiatives here. Other hotels introducing building management systems, and a variety of other examples and innovations available to cut cost while increasing environmental responsibility and energy efficiency in the hospitality industry. We've also been invited by the European Commission to participate in the Romania and Climate Change Conference here in this hotel with an exhibit on sustainable construction on the 26th of February. We will have roof gardens, green roofs, and urban landscape on March 10th. On March 19th, we have sustainable construction materials training event about the opportunities and necessity for creating more environmentally friendly building products. On 23rd of April, creating greener workspaces, office design that is both functional and desirable, and green. In the middle of May, we've been invited to present our activities at Architecture Days by the Association of Student Architects with the Technical University of Cluj. And we have more events in the planning stages. And to answer the question, how can one get involved? For those companies that have not yet joined our council, we would like you to consider joining our efforts to bring environmental responsibility and economic opportunity to the building industry. And you can ask my RoGBC colleagues here today or find more information on the website on how to do that. And we know that even with keeping costs low, it can be a challenge to participate on a student budget. And therefore, we have created associate memberships where students can volunteer their time in exchange for a valuable learning experience and free entrance to our future events. And lastly, I'd like to say once again a sincere thank you to our founding members, and these are listed here, and our new members joining in 2009 for your commitments to our efforts. I would like to now briefly introduce our two speakers for today, Ms. Aurore Julien, and the head of sustainability for Llewellyn Davies Young Architects, and Professor and Doctor of Architecture, Ms. Ana Maria de Bija of the Jan Mincu University of Architecture and Urbanism. And you have their details listed in the agenda, so I won't go through their list of significant accomplishments, but I will tell you that both have been very enthusiastic about accepting the challenge to create this curriculum for the workshop and to create an offering that is both relevant for Romania and includes leading design principles from around the globe. And Ms. Julien and Professor de Bija, we look forward to your presentations. Thank you.
The presentation is being started. So my name is Aurore Julien. I work for Llewellyn Davies Young, which is an architects company in London. We do a lot of international work. And the design director, the gentleman whom I work with, is a gentleman called Kan Young, who's a relatively famous architect from Malaysia. He's one of the fathers of bioclimatic design. And he started designing large-scale green sustainable buildings in the 70s, which is probably not, it wasn't the first one starting designing green buildings. I think green buildings have been designed since the time we started designing buildings, but I think he's the first one of the first people to reintroduce that within the large-scale buildings area. So I'm going to start this presentation, if I can manage to work this machine out. Is it? No. It doesn't do it. Whoop. Okay, I just took it the wrong way. So today we're going to talk first about bioclimatic design this morning, and we'll explain a little bit what it is. And this afternoon we're going to have a session talking about the management of green building design. So this first session on bioclimatic design, we're going to explain a little bit what bioclimatic design, why do we need bioclimatic design, what it is, and then go a little bit more in the depth of it, looking at daylight, well, natural ventilation first, daylight and sunlight, and we're going to finish by looking at how the bioclimatic design process works, how we can integrate bioclimatic design within the design process of buildings. This is an interactive workshop, so that means that we're going to ask you to do some work, and that's really good for me because I can rest when you're working. So the first section is about why do we need bioclimatic building to design green buildings. So I'll start with the question, which of these buildings are the greenest? So I've got a series of huts. They're all made with very local materials. They're using very little energy because generally they have very little heating if they do. They've been made with local staff, so they're very, I think they're relatively green buildings. Then I've got a series of buildings which have been designed by my boss. These are skyscrapers. They're bioclimatic buildings, so they are very well shaded, very well lit, and they use little energy. This is a building in Singapore. And this is a competition. It hasn't been built for obvious reasons, but this is a sort of theoretical exercise, I would say. Then we've got another series of buildings. Well, actually, I've just got one. This is a nuclear bunker in the north of England. And one could say that it's actually quite a green building because it's made essentially, except for the air conditioning systems inside of it, for natural buildings, it's covered with green roofs. So does anyone know which one of these buildings is the greenest? No? Well, it's the huts. And the reason why it's the huts is because the huts, well, partly, of course, they use very little materials. It's only local materials, but also there's very little heating, ventilation, and air conditioning in them. So if you go from this scale, from the left to the right-hand side, on the left you've got nothing at all. So imagine maybe in Thailand on the beach and there's no building. Then we've got the hut through the passive building. The passive building doesn't have any heating or cooling. The bioclimatic building, which I believe is the next step, which is a building which is air-conditioned and which has heating and ventilation, but which is made in a way which is going to reduce its own energy use. The next step is the air-conditioned box, which is a lot of buildings in Dubai currently are being built like that. And finally, we have the nuclear bunker, which has probably the most amount of heating, air conditioning that you can ever imagine. So the more you go towards the right, the more energy use you get. But one could say, well, if you get more energy use and better ventilation, etc., then it should be more comfortable. We think that it's not the case, because if you're in a bunker or in a glass box, then you're probably not so comfortable. We think that actually the best comfort zone is the area where you have a sort of relationship with the outside, and is a building which actually reacts with the outside. So what I think is that the most comfortable building is a building which is bioclimatic, which sort of interacts with the external, with the outside. So the gentleman on the bottom here is my boss. And what he says is that there's two justifications for bioclimatic design. One is for saving energy, and the other one is for people's comfort. So I think so we're not only talking about energy saving once designing a bioclimatic building, we're also talking about buildings which are comfortable, which are healthy, and good for the occupants. Therefore, more valuable. So now we're going to go through the principles of bioclimatic design, and then Maria is going to present on this.
One of the things that the presentation begins with is the definition of the bioclimatic design. You will allow me to sit, please. Right. What is a bioclimatic buildings? And why do we deal with them? One of the reasons is that the building sector is responsible for almost 40% of the total energy consumption on a national level. And energy was produced by burning fuel, and you can see the image, which is rather horrid. Corresponding liberation of CO2 leads to the greenhouse effect. We begin with two definitions about bioclimatic architecture. It is a way of designing buildings and manipulating the environment within buildings by working with natural forces around the building, using them, actually. It's from the Manchester School of Architecture. Architecture that designs to take advantage of climate and environmental condition is another definition that I really liked. And what is very interesting in mostly all building concerned technologies and systems is that we don't really discover them now. But actually, we rediscover them now because in the antiquity, they were existing. The Greek had their houses oriented towards south. Socrates has lived in a solar house. Aeschylus said that you have to be stupid to live underground. Well, actually, we can have a discussion here because the underground buildings are very comfortable and very modern today in many respects. Going a little bit further, the Romans carried out the Greek principles with the heliocaminus. Direct translation would be a solar furnace. Actually, they were heating their water for the baths. We forgot in the Middle Ages about this principle and reinvented them in the previous few decades. So what natural environmental agents influence a building from the bioclimatic point of view, of course? Sun, air movement with the wind, water in all states of aggregation, liquid, solid, and gas. We have to build using them and helping ourselves with the benefits that these environmental agents bring us. Also, vegetation, plants and animals help us. So you have all these presentations within your folders, so I can gallop through the presentations because it's a very dense day. Sun, air, movement, water, and biological agents, I said, with their advantages and disadvantages: health, hygiene, natural ventilation, which again means health, natural cooling, which again means health, health brought to us from the plants, and in all the first three situations, we help ourselves to the natural energy that can be produced by using these agents. And of course the disadvantages, because we have the thermal discomfort, we have storms, we have floods, we have deteriorations in all the cases of misuse of these agents. And so, sun, air, movement, currents and winds, water, landscape, vegetation, all determine the location, the orientation, and the geometry of the building. They should be, the building should be determined, the position, the orientation, the geometry by these agents, using them for us and not against us. The architecture has an influence over the energetic performance of the building, the geometry of the building and of the envelope, and the building materials and structures determine the thermal behavior of the building. The images that I have taken, and you can see the source of illustrations, are very explicit. You can see how a building can be built in the vicinity of vegetation. You can see how the wind passes over and not through the building. You can see how during the winter time, sun goes in the house through the branches, the leafless branches, and during the summer, how the shade is protecting the building against the sun. You can see how the accumulated heat during the day is given back during the night to the environment. Passive gain. Sunlight is admitted through the space, through the south-oriented, mostly sun-oriented windows, and you can again see the positions of a utopic building. During the winter, energy is collected in the walls and reversed at night. During the summer, sun should be kept out by means of solar protection, and in a very, very simple way, by just drawing the two rays that represent the winter sun angle and the summer sun angle, you can actually design in a most simple way the solar protection for the summer dimension and the possibility of entering the sun during the winter. And of course, I couldn't resist the temptation of showing that actually vernacular architecture, and from there on even civilian architecture, Romanian architecture, because we we have this workshop here, it has always used, and not only Romanian architecture, all the vernacular architecture uses principles of bioclimatic design, because they had to build with the nature, not against it. The use of passive system is the most efficient way of taking advantage of natural resources. Technology uses sunlight to provide renewable energy, and the way the technology works in the stages you can find in the slides. Not exactly bioclimatic design, but I did say that we use water power, solar power, and wind power in order to produce power. And we can see them here in the slides in the traditional and in the contemporary way. About natural ventilation, the benefits are physical, mental, and more about the natural ventilation will be presented. So this slide is just flavor of something that's going to be a little bit later. But building with vegetation brings a lot of benefits, shields the house from noise, reduces energy consumption of the house by shading the house, as I mentioned before, cools and humidifies and filters the air, provides an attractive and relaxing area. I would very much like to have a coffee on first slide, location. Rebuilds the natural environmental balance, logically, because it brings back the plants and the small animals that were in that environment. Bioclimatic design takes into account local climate and includes the following principles: heat protection of the buildings in winter as well as in summer by adequate insulation, air tightness, shading system, colors, reflections. Removes the heat which accumulates in summer by passive cooling and natural ventilation, uses solar energy for heating buildings in the winter season and for daylighting through orientation, space layout, passive solar systems, solar control for daylighting, solar protection, the use of local building materials, which is very important, as well as recycled or recyclable materials whenever possible, the use of local vegetation in order to preserve or restore the local natural environment by diminishing pollutants and CO2 emissions. So in conclusion, bioclimatic architecture is an evolved version of popular architecture, vernacular architecture, accomplished with contemporary means, which means building techniques, advanced energy concepts, and modern mechanical devices. This is a scheme, and thank you.
So I'll continue after, thank you very much, Anne-Marie. This little presentation on the bioclimatic design, on how to go ahead with designing a bioclimatic building. So obviously, because the bioclimatic building is at one with surrounding nature, it kind of supposedly it interacts with the climate outside itself. Then the first thing to be knowing is the climate. So of course, if you're building a building in your own region, you think that you know the climate really well, but maybe not. So the first thing is to be looking at the climate in which you're building your building. Then trying to understand the microclimate and the site itself and how the climate is being affected by the local environment. And also it's important to look at the site conditions. So that might involve things like the local pollution. So maybe if you're naturally ventilating your building, you want to know where the pollution is. So if you have a road, that's part of the site analysis. That's part of the microclimate that you need to know about. Then from that, we derive the layout of the building. Then next, its actual form and its internal layout. Then we look at the facade. And the last thing that comes is the eco-engineering, or the engineering. My boss calls it eco-engineering, I call it engineering. The last thing that we bring to the building is the engineering. Although whilst we're doing all this exercise, we might have a good idea of what type of engineering, what type of system are going to be used on our building, but it is the last thing that we design, it should be. So these are just very small, like for the example of little studies that we're doing or that can be done in the bioclimatic design process. On the right low-hand corner there, you have, this is just a little study of climate. So we're looking at the average temperature, when does the sun rise, and humidity, wind speeds, wind direction. That's all the things that we're looking at when we start wanting to design a bioclimatic building. Then we're going to do some shape studies, some form studies. And the final thing that happens, we might do a little bit of simulation of, I don't know, how much sun we get on the different parts of the facade or how much wind arrives on the facade to be understanding a little bit more in detail how our buildings behaves. The thing is that happens last. The first thing we do is we're looking at the climate locally. These are examples of small climate studies that have been done on the project. These are wind data, which it's in Abu Dhabi, so that was something that we did for one of our projects in Abu Dhabi. What we were looking at is the relationship between the wind frequency and the temperature. And the reason is maybe there's some very small areas. I mean, Abu Dhabi is certainly not the first place you'd be thinking about having a naturally ventilated building. But maybe you want to know about wind direction and wind temperature at certain times of the day to be evaluating whether external areas could be comfortable and to be seeing whether you can make some external areas comfortable at certain times of the year. So that's not all the year, it's just certain times of the year. So in this particular case, the result was that there is probably not such a strong relationship. So the second line here looks at direction of wind and temperature. The darker it is, the hotter it is. And we just saw that there wasn't really much a relationship between the wind temperature and the direction of the wind. It's not the case everywhere. It's very different in the UK, for example. The one at the bottom here is looking at the relative humidity and the wind direction. So in many places you may have, for example, northern winds being colder, and you might want to take advantage of that to be making sure that your building catches that cold wind when it's too hot. These are further studies. All these studies have been done with a software called Ecotect. That's the one that we're using in our office. You might be wanting to investigate other tools. It doesn't really matter what you use. I quite like Ecotect because I think it's quite a complete tool. It does everything that I needed to do at the early stages of project. The little graph on the top, I'm going to use this thing if it works. Yes. This little graph here, this is looking at the amount of solar radiation, how much solar energy we get in different orientation. So for example here, for two different, so the red lines would be summer and this would be winter. So this, I believe, I haven't checked, but I think this is on the other hemisphere. This is the other side of the planet. But the point is that you can look at, for example, the orientation, the optimum orientation of a facade. What is the best orientation in this area? So that probably would be towards the north here because we're on the other side of the planet. Because you have the highest solar gain in winter and the lowest in summer. So these kind of little studies are really, really important because this is what will form our building. This is what helps us to form our building. I mean, the thing is that, okay, here I've been using this computer software to tell me that, but we actually know, and that, for example, in our hemisphere, on the north hemisphere, the buildings need to have as much glazings towards the south facade. It's something that we know, something that has been developed through traditional architecture. But when we don't really know, when we want to know it in a little bit more detail, then it's useful to have the software. This little graph here is it looks at the variation of temperature during the year. Each section here is one typical day. So through that, you can look at the difference of temperature, the typical difference of temperature in a typical day. So if you have a wide temperature range, then you know that your building may take advantage of night cooling, for example. So if you ventilate at night, you're going to get, you're going to cool down your building, and you can take advantage of that during the day if it's very hot. So just through this climate analysis, I know in this particular area of the world that there's a good chance that I can do some nighttime ventilation, and that natural ventilation could work quite effectively in summer. This is just another graph that shows temperature variation along the year. If I'm going too slowly, please look really bored or do something that indicates that you know all of it. This is another type of analysis which is being done with the same software, actually, but again, this could be almost done manually. This is a psychometric chart. I don't know if you're all very, very familiar with that, I'm sure, to an extent. So we're looking at the temperature at the bottom, and this is the humidity with relative humidity lines there. I mean, even if you if you're not particularly familiar with this, I don't think this is the right time to get familiar with it. But the general idea is that the blue spots in the middle, if this works, the blue spots here indicate the frequency of occurrence of different temperature and humidity ranges. And so we can sort of decide the yellow bit here is the area where people are naturally comfortable. So if the blue bits are within the yellow box, then it means that we are comfortable. Now, what I can see from this particular climate analysis is that the blue is really quite a lot outside the yellow box, and it's not very comfortable. Most of the time, it's too hot and too humid. So what we can do is, through this analysis, which is carried out by the computer, is we can look at the impact of things like natural ventilation or passive solar design. So we can look at the impact, how these passive measures can bring the temperature towards the comfort range. So let's say, take the example of natural ventilation with nighttime cooling. We ventilate the building at night, the building gets really cold, and so without any addition of sort of air conditioning or heating systems, we can cool down the building itself to bring the comfort range of the day towards towards an acceptable range. So again, this is not an exercise. I haven't designed my building yet. It's something which I do initially, just to be looking at what kind of measures can help to bring my building to the comfort range without any air conditioning system. Now, the thing in this particular area is that we can see that, so these boxes here represent what range I can bring back to the comfort range. This is a very rough study. It's not, you know, once you add the internal loads, or once you know a little bit more about your building, then the results might be slightly different. But what it tells me is that there's quite a lot of the occurrence of temperature and humidity that I can bring back to the comfort range here if I don't have any internal loads. But there still is definitely a need for air conditioning or some form of system there. So to be able to get climate information, there's a variety of sources. the software well, many of the software that we're using, and this is just a few of them. I don't want to do advertisement. If you investigate, you will find there's a lot of other types of software that can be used. But the software that you can use to do building analysis always tends to have climate data, climate information. It might not have climate for the area which you want to study. And if that's the case, you need to go to the Department of Energy website, the American website, which has an unbelievable amount of information on climate, and it has all sorts of climate files that you can download for all around the world, really. Then there's another file, another software which is called Meteonorm. Meteonorm is a very useful. It is the software itself is geared to do climate analysis. So that's the only use of the software. What it does is that it has a database of information on climate data for different areas around the world. But what it does is that if it doesn't have a certain information about a certain area, it kind of averages the areas around it, which you've got to be very, very careful about, because of course, if you're looking at wind data and you have a large mountain near your site, you don't really want an average information between two different sites. What you want is the specific location for which you're studying. So I think Meteonorm is a fantastic software, but it's important to be quite careful. And the last source of information on climate is Google. I use Google a lot. I mean, even if you don't have a full data file with hourly data for your area, you can get on the touristic website, and you get a good first idea of what the kind of temperature and humidity you get. It's very useful. There's also very often information about local particularities, like local winds that may exist. For example, we have some very interesting winds occurring, I don't know, in the Middle East, and I found about that on Google. So Google is a very good source of information, I think, or any search engine. So this is my health warning when dealing with climate analysis. It's important to check the source of the climate. It's very important to know where the information comes from and to know whether it's a reliable source. The second thing is it's important to be very careful about wind data, especially if you're using any kind of software which is going to average the two locations around it and calculate wind data from it, because that means that your wind information might be really wrong. The other thing is that it's important to be understanding what kind of climate information we're dealing with. The thing is, if we take a certain, oops, this is not going well. Sorry. If you take a data file, it's going to have hourly information on climate. But it could be for an average year, or it could be maybe for a very hot year. So there's different types of file. I think it's very important to be aware of what kind of information we're dealing with. You might, if you have some information, background information that tells you that it's a especially hot summer year, which some information is actually taken for that purpose, then it means that it might be a safe information to be using if you want to design for summer natural ventilation. If you have an average year, then maybe that's a good climate to be looking at, to be evaluating energy use of your buildings. So I'm talking already, I'm stepping ahead, because what I'm telling you there is that the climate files can be used for other purposes than actually just looking at the preliminary design before designing your building. But we'll go, a little bit later, we'll go through different other uses that you will find of climate information. And the last thing to be remembering is that microclimate and climate are two very different things, and that the climate of a whole nation is not representative of the different little locations in it. So you have to be really aware of the particularities of your area, and also even of the particularities of your site. If you're into a hole in the ground, then you won't have as much wind as you'd have about 10 meters to 100 meters further. So I think it's important to be really aware of what's going around on the site and in the very small area that we're dealing with. So just check the time. My next section is on natural ventilation. I think I'm a little bit early, so it's really good. So this is a slightly separate. I'll talk through the design of naturally ventilated buildings and natural ventilation. So why natural ventilation? Why ventilation? Obviously, is to get fresh air, to remove smells and pollutants, and to cool down buildings. This presentation is going to be a little bit long. So the first, I think Anna Maria went through that a little bit earlier, but the advantages of natural ventilation is, of course, that it's low energy. It's a very simple system. What is simpler than just opening a window? It tends to be cheap, although if you start having very complicated controls to automatically regulate the opening and closing of your windows, and suddenly it gets quite expensive. It tends to be low maintenance. Again, if you start having automated controls controlling the opening and closing of windows, then it can get a little bit high maintenance. And it's quite healthy. It's really healthy to have direct contact with the outside air. The disadvantages is that it's not so reliable. I think from the point of view of an M&E designer, of a building services designer, it's not a very comfortable thing to be doing, to be telling, say, your client that your building is going to be having a variable temperature inside. And it's difficult to be guaranteeing that the temperatures inside the naturally ventilated buildings are not going to, that high temperatures are not going to occur very often. I think it's a very high risk because you don't know exactly what the temperature outside are going to be in the next 5 years, say. It doesn't allow for high occupancy or high internal gains. I've designed a building, like the first building naturally ventilated building I've designed. It was quite amusing because the first year the building started working, it worked extremely well. And then we had quite a nice, cool summer, so it was really good. And the second year, my client called me back and said, "Oh, I want to put more people in the building. I want to put twice more people because we're growing, and I think the building can actually fit twice more people." So suddenly, I had twice more heat inside my building, and my building stopped working. I mean, I did warn the client. I say, if you put more people, the natural ventilation won't be enough to get rid of the heat inside the building. So there is a little bit of a risk in terms of how much people you can fit in a naturally ventilated building. There is a limit, and it's very important to be aware of that limit. It doesn't mean that naturally ventilated buildings are bad. It means that they have a limit to how many people they can take, or how many computers, or how much internal gains. The other disadvantage is that, and I'm not sure if it's a disadvantage, is that whilst the building is being naturally ventilated, then the comfort conditions inside it are going to change. They're going to vary. And at the moment, we tend to want to design buildings to be at 22 degrees or 20 degrees centigrade. This is actually based on a very wrong theory that our comfort zone is at 20 degrees. The reality is that our comfort zone varies depending on the external temperature. So the fact that the temperature inside a naturally ventilated building varies, I don't believe, and well, it's actually supported by science, it is not a problem, as long as it doesn't go over a certain limit. There are some design limitations whilst designing a naturally ventilated building. There is a limit that tends to be, to design a simple naturally ventilated building, there tends to be a limit in the depth of the rooms which we're dealing with. It tends to be a very important thing to have thermal mass, to have hard surfaces inside the building. So there are some design limitations. And of course, noise and pollution. If you open the window to the outside, then you're going to be more affected by noise and pollution directly outside your window. It's quite obvious. Although, again, there are ways to be dealing with that. There are certain systems that can be used to be preventing the noise, to be preventing noise from getting inside and pollution to get inside. So I'm going to go through the main types of natural ventilation, and this is very simplified. So really, there's two different forces that drive natural ventilation. There's a stack, which is heat-driven, and then there's wind. And there's two ways to get wind. There's just directly through wind pressure, so the wind gets straight into the building, and the other effect is through venturi, where there's a suction effect, which is being used to drive the ventilation. So this is really the main types of natural ventilation. There are variations between the two. There are systems that use both of them together, or the three of them together even. So the most simple way to naturally ventilate a building is through single-sided, just a window on the side of the building. Then the more effective way is to have a window at the bottom and at the top, because then you're taking advantage also of the stack, of the difference in air pressure due to the temperature. Then cross-ventilation, and then you can start having more complex systems with, for example, a mix of stack with a solar chimney, which is a chimney using with a glass front, maybe. And then you can use internal atria kind of shapes, which use both, it actually uses stack, venturi, and a little bit wind pressure. So this is an example of a solar chimney. The building on the right is in Nottingham, I think, in the north of England, near Nottingham. This particular system is using a glazed area to absorb solar energy to ventilate the building. Now, I got my doubts about how that works, actually. It's funny, I'll go through another building quite a lot towards the end of the day, which we've designed that's got a solar chimney on it. The problem about solar chimney is that if the surface of the glass is really cold, then what happens is that the wind actually falls because it gets cooled and it falls inside the solar chimney. So the chimney sometimes doesn't work so well. So very often these solar chimneys need a fan, which means that it's not quite natural ventilation anymore, so they're cheating. But it is possible to design them properly to make them work. But to be able to make them work, I think it's very important to be doing a full simulation, or to be doing sort of testing, proper testing, to be able to understand whether the system is going to work. So generally, what's used is a CFD, computational fluid dynamics simulation, which I'll explain a little bit more what it is later, to be seeing if that kind of system works. Wind catcher, I've got, this is in Middle East. Wind catcher, it's not very new technologies, but they've been used for centuries, as you can see. The general idea is that you have a sort of, I've done it again. Oh, yeah. You have a sort of, it's like a chimney form, but it catches the wind, basically. It's got 4 different walls inside it. It can be any other shape, and the wind is caught and just falls inside the building. The good thing is that the wind can come from any direction. That still works. On the other side, so say if the wind comes from this side, the air goes out from the other side through venturi effect, partly. So it's a system that works extremely well. Sometimes it's combined with, I don't know, water spraying, or a bit of body with water in it to cool down the air further. So, yeah, this kind of system works extremely well. Many are still in operation, and it's perfectly sort of reasonable to do sort of to do modern versions of these systems. This is a very ugly picture, But what it's looking at is just looking at a sort of wings, oops, I don't know, wings which catch the wind. So really, when you open your window, if the wind comes from this direction, you catch the wind, it kind of catches the wind, and the wind comes out from the outside. It's a very simple system, but it is possible to be, if your wind, say, comes consistently from the side of the building as opposite to straight in front of it, you can sort of make build these little wings that are going to catch the wind and enhance the natural ventilation inside your building. But to be able to do that, and to be able to know whether that's necessary, it's important to know where the wind comes from, which is why your climate analysis was so necessary. I won't go through this in too much detail, but there are, I'm sure you're aware of double facade ventilation systems where the facade itself has 2 layers and is ventilated internally. The facades can be opened or closed in different sides. So it can be open to the outside when you need, say, a little bit of cooling, or it can be open to the inside if you want to reuse the air. So through the dynamic behavior of the double facade, you can both naturally ventilate your building and ventilate your facade to cool it down or use it as a buffer. These particular systems, again, to be able to understand whether they work, I think it's very important to do very detailed studies, because they don't always work. And the tools which are being used to be evaluating their performance is computational fluid dynamics tools again. So now I'm going to go through some rules for designing naturally ventilated buildings. So, as I was saying earlier, the problem whilst designing natural ventilated buildings is the internal loads inside the building. So, the amount of energy inside the building. So, it's important to make sure that if there is internal gains, important internal gains, like if you have a printer room, then you might want to isolate that printer room and to have it in a corner which is actually air conditioned, so that the heat from it doesn't come inside the rest of the building. So this is an example, but it's very much the part of the way a naturally ventilated building is designed. Is the different rooms and the different users are being separated, not just through their function, but through their thermal behavior, how much heat gains you have inside them. Low energy everything. So you need to have low energy lighting. You need to have low energy screens for the computers. And sleepy people as well. But you need to have low energy systems inside your building so that you keep the internal gains as low as possible. The shading system is also very important, especially on the west and east facades. And the thermal mass inside the building should be kept to a maximum, especially if you're ventilating at night. These are the different types of windows. When designing windows, I think it's very often true that there's a designer that's going to design a naturally ventilated building, and then the architect comes around and say, well, my window is actually a type of window like, oops, I keep doing this, a type of window like this. And so the area of opening that you're going to have is about half of the area of the window. So when designing, again, naturally ventilated building, it's important to keep in mind what the window is going to be like. Because if you need a certain area of window opening, a certain opened area, that's not the area of the window. That's the area of the open bit of the window. Even though, because there's actually some other coefficients that should apply. But I think it's a very silly thing, but it's how many naturally ventilated buildings fail. It's because this little detail is forgotten about. Another thing is, if the building is ventilated at night to cool it down, the opening of the window needs to be thought about very carefully, because there might be some safety issues. So, for example, or there may be also some safety issues, so people don't know, do silly things like throwing themselves outside the windows. In schools, for example, in hospitals, there are limits as to how much, in the UK, I don't know about here, there are limits as to how much you can open a certain window. You can only open it, I think, by about 10 centimeters. So whilst designing the naturally ventilated building, it's important to keep aware of the opening window margins that you may want to have or that you may have, especially if you're leaving the building open at night. You don't want people to get in. This is really what thermal mass does, which inside a naturally ventilated building. So if you look, let's imagine the blue line is external temperature. So it varies. It's kind of hot during the day, cold during the night. And you have all the hard surfaces inside the building that are going to collect the cold of the outside and that are going to temper with a certain delay the temperature from the outside. So it basically brings your temperature to the comfort range. Sorry, I just forgot something. To be able to get this effect, of course, you need to avoid carpets and false ceilings because that's going to cover the thermal mass and your building is not going to cool down as effectively. These are the kind of guidelines that we use. These are UK guidelines. I know they're being used in the States as well. I don't know if you have any equivalent rule of thumb that you use to be designing naturally ventilated buildings. What we use is that if your building is side ventilated, is just one window, then the width of the room that you're ventilating shouldn't be any deeper than twice the height from the floor to the ceiling. If you have a top and bottom opening, then the ventilation is more effective. Then the width shouldn't be any more than 2.5 times the height. And if you have two side ventilation, one window on each side of your room, then the width shouldn't be any more than 5 times the height. So these rules basically are what sort of govern the form of naturally ventilated buildings. What's important to notice here is that the higher ceilings you have, the better. And also it makes a very nice feeling to the room. But the higher your ceilings, the more the natural ventilation is going to function. The other thing is that you're going to end up with quite narrow plans, which is why in Germany many office buildings have narrow plans, so that you can allow for good daylight and good natural ventilation. The wind-driven natural ventilation is slightly different, of course, at high levels and at bottom of the building. So if you have, say, a high-rise building, then you're going to get a lot more air through wind-driven ventilation at the top than you get at the bottom. It's quite obvious, but in theory, that should, if you have a naturally ventilated building, it should result in smaller windows at the top than at the bottom. The thing is, very often buildings are not designed for wind-driven ventilation. They're designed for a ventilation which is only driven by stack, by temperature difference. And we do that because it's a safe thing to be doing. Another important thing is that the wind speeds are going to be very different in cities than they are in open land. You get more wind at the bottom in open land than you get in cities. The wind is very slow down at the bottom in cities. And that's quite useful to know as well when you design wind turbines. So these are some of the equations that govern the design of naturally ventilated buildings. There's 2 ways to go about it. So first of all, there's 3 things to do. The first thing is to use the rules of thumb, which I was mentioning earlier about the width of the building. And the second thing you might need to do is to do a hand calculation using these formulas. There's a calculation method in a document which I think you have reference of, which is a kind of UK document, which is called the AM10 design. I think it's called Design for Natural Ventilated Buildings or something like that. But through these equations, it's possible to be evaluating the size, the required size of your windows depending on the heat gains inside the buildings. So they're very simple equations. I mean, they look complicated like that, but once you've done it, it's okay. And they will give a first-hand idea of how big your windows need to be and what kind of heat gains you can cope inside the building. And very often, I don't know how it's here, but in the UK, very often people don't do that. They go straight into doing simulations. I won't go through this too much, but I mean, the general idea is that there is a kind of neutral pressure point that occurs, and through evaluating the pressure differences from top to bottom at different levels of your facade, through both stack and the use of wind pressures, you can evaluate what is the point where the air, what air movement and what air quantity you can have inside your room. So I'll go a little bit through some important design thoughts. Here we've got a building which is naturally ventilated through an atrium. So using stack here and using a little bit of venturi effect. And so if the wind comes from here, we're going to get high pressure here, negative pressure here. The thing is that many buildings are being designed like that, but it's important to be aware that if the wind comes from, is very strong, then what might happen is that actually you don't really get what you want. You get air coming straight through your building. And that only happens if the wind is strong. Now, I don't think that this is a problem, actually, because this is, without the wind and with the stack effect, is a kind of worst-case scenario. It doesn't really matter so much if at some times you get the building doesn't function the way you want it to. But it's important to be aware of it, because you might want to have different closing and opening window regime, and in terms of the way you're going to simulate the building, maybe you're going to think slightly differently. This is another case. So I'm sure you can get what's going to happen now. The wind comes from here, what's happening? Well, you get a positive pressure on here and a negative pressure on this side. And it might be that some air gets through the wrong direction and it's harder for the wind to get up there. This is a bit more of a problem because it can actually prevent your building from functioning. So I'm going to go through some examples of buildings, some of which I've been working on, some of which we haven't been working on. This is a building that Ken Young has designed. It's a bioclimatic building. It's got a completely different shading system on different facades of the building. Sorry, I should have said this is in Malaysia, in Kuala Lumpur. And it also has, what's interesting, it also has a natural ventilation inside it. Now, it's quite a famous building for its natural ventilation, but being in Kuala Lumpur, you would imagine that natural ventilation is only limited to certain types of space. So this building has mainly the core and functional areas naturally ventilated. So all the office areas are generally air conditioned most of the time. I don't think that's a problem. I think it's a very good thing to have some of the areas that are naturally ventilated and some which are not. You just do what you need in the areas which can accept. You just put natural ventilation in areas that can accept natural ventilation. It's not necessary to have the whole building. So cores, staircases, etc. don't need air conditioning all the time, so it's possible to do that. This is a relatively famous building, which I'm sure you've heard of. This is a quite complex system of well, also not so complex system of natural ventilation here. What's I think quite interesting here is that there is a internal gardens, which are also natural ventilated. And one thing which I should not actually mention is, if you look, despite the quite the quite deep internal spaces here, the actual depth is not so much. This is a building in the UK. Now they've done something quite nice. It's classrooms. So classrooms and any seminar areas or any areas where there's a lot of people coming in at the same time are generally very difficult to naturally ventilate. And so this particular one has a system by which the air is being evacuated from the area just underneath the roof. The air comes in here. Because it's cold, it's in the UK, remember? The air falls down inside the classroom. The people heat up the air goes up to the area just underneath the roof, and there's a ventilation area just at the top. I went in there, it's actually nice and comfortable. And so the other thing is the roof area here kind of acts, because it's of its orientation, acts as some form of solar collector. So it's gonna, the roof itself is gonna heat up a little bit and help in sort of rising the air and getting rid of the air here. This is a building which one of the buildings I've worked on the design of. This building is, the problem with that one is that it was a lightweight building. It's timber and it's all lightweight materials, which means that there's no thermal mass. If you ventilate at night, it doesn't cool down. It stays at the same temperature. And so I had a very big problem because there was quite a high occupancy of people. And we didn't want to use air conditioning in there. So what we did is we've got, well, first of all, we've got an extremely, I mean, I'm sure you would have noticed that the shading system is quite substantial. So this is just to prevent heat gains inside the building. They're also quite a light color, which means that the light will sort of come inside the building quite easily. And inside here, these blocks here that you can see, these are sort of connected to an internal atrium kind of space. And when the air was coming almost only, the wind was coming from the two sides of the building. It wasn't coming from the flank here, it was coming, sorry, from the front and from the back. So these things here, they open and close depending on the wind direction. And what they do, they don't open to catch the wind. They're not wind catchers. What they do is that they use a venturi effect. So they open in the opposite side of the wind. So there's a venturi effect where the wind comes, the air comes from the building to outside. The other thing that we've done, it's only 2 stories, and we've raised the floor a little bit, and for the bottom floors here, which have a higher internal heat gains, there's more people and more computers, we've taken the air from underneath the floor. So the air goes underneath the building, uses the thermal mass of the ground, and comes inside the building through vents in the floor. And that works extremely effectively because then there's a kind of cool body just underneath the building that's being used to cool down the building. The only problem with it, though, is if you have gaps into the floor, you cannot put any furniture onto it. And I was a very young designer. It was my first ever design building, so I didn't think about that, and nobody mentioned it until the client again came up and said, you know, I want to put furniture onto your vents on the floor, and can I do that? And of course you can't, because that's the ventilation of the building. That's like shutting off the air conditioning system. So this building works as long as you don't put furniture onto the gaps into the floor. This building has been designed completely, through exactly the method which I was mentioning, climate analysis. Then we did we used the guideline, the rule of thumb. Then we did a hand calculation of the size of windows, and then I did a full-blown building physics simulation to simulate the performance of the building. This is a rather famous natural ventilated building. I'm not sure about this. I want to visit it as well. I've got a problem with it because it gives a bad name to naturally ventilated buildings in the UK. Architects in the UK don't like the look of it. They don't like the way it looks. And so very often they sort of criticize naturally ventilated buildings as being ugly using this one. So I don't know whether it's ugly or not. That's not my job. I'm an engineer. I don't deal with architecture. But in any case, I know that it's been given quite a dodgy reputation. So what this uses, the problem with that building and the problem they had is that they wanted a deep plan building. They couldn't design with the limitations which I was mentioning earlier. So, the depth of the building here was compensated through the use of extremely high, and you can see this one here, stacked chimneys, to be able to create a sufficient force of air being drawn from the bottom here. Now, when we do that kind of thing, obviously you can break the rules which I was mentioning, the rules of thumb about 2 times the height if you have one single side ventilation, or 5 times the height if you have 2 sides ventilation. So if you do stuff like that, you can definitely break the rules. But to be able to break the rules, you need to carry out quite detailed calculation exercises using both hand calculations and complex computational fluid dynamics simulations, and that's the way they've done it. Because we don't have instinctively the knowledge of, you know, how much air is going to be drawn from that point to that point, basically. It does work quite well, again, this building. It's a very comfortable building. It's, however, has these enormous chimneys at the top, and it's all automatically controlled as well, obviously. So you have temperature sensors that open and close the doors of the building and decide when to ventilate it. This is the Building Research Establishment Office. The Building Research Establishment is very well-known in the UK organization. They are the origin of a system called BREEAM, which is the equivalent of LEED. I'll explain more about this a little bit later. Because there is a building and research establishment, they have to set the good example in the UK. So they keep doing loads of innovative things. What they've done here, they wanted to have a natural ventilated buildings, but they wanted to be able to put inside the buildings, to have walls, to have cellular offices if necessary. So that's a little bit of a problem, because if you have, say, a room like this one, or half of this one more realistically, and you want to have cellular offices, then what that means is that you will cut the flow of air from one side of the building to the other. So they had to think about a way to be able to bring the air inside the depths of the building without losing the ability of having cellular offices. So what they did is that they sort of did this kind of shape of wavy ceiling, which is all in concrete, so it has really high thermal mass, and the air comes through the wavy ceiling from one side to the other, basically, with different areas where the air can come out. So again, it's quite, I mean, if you look, the air can go through gaps in between the ceiling, basically. So it comes and goes. This is, again, quite an effective, it's quite cold, actually, in there. But it's a very effective building. The only problem, I think, is I'm not sure, but I suspect they might have little fans, again, because they do have these solar chimneys, which are, again, covered with glass. And when I went there, it was working perfectly, but I don't know whether sometimes in the winter the air actually wants to go up the chimneys. It might be that it goes down. But again, this kind of function can only be checked through simulation or little model. And this is another building which I've worked on this. I haven't been at the origin of the whole design because it's huge, but I've worked on this a little bit. It's a National Assembly for Wales. It's been designed by Richard Rogers in Wales, and it has basically, because it's National Assembly buildings, there's sort of these areas here where the meetings occur, and these areas are naturally ventilated. These huge things, which I think are about I think they're about 5 meters high or something like that, totally. These things are wind coils, so they direct themselves depending on the wind direction. They actually turn, and they used to be dry, again through a venturi effect. The air is being drawn through the building from bottom to top. This is one of the buildings that has taken the most work in terms of natural ventilation design that I've been ever coming across. And this was enormous amount of simulation work, weeks and months of design behind that. This is a very famous London building, which I'm sure you would have seen pictures of. Is the Gherkin. It's been designed, the shape of it has been designed so that the wind kind of flows around it in a kind of smooth way, and also so that the wind doesn't come down through a downdraft. It has to go around it, so there's no downdraft here. There's advantage in doing that, and one of them is that you have a more regular wind pressure around the building, which gives a more regular amount of air coming inside the building. One thing which you might not have known is that there are openable windows all around the building. So you have, again, if you look, there's a core area, but the actual usable depth of the building is not so much. The air comes through and around the building like this. What's quite interesting is, okay, a lot of design work, haven't worked on this obviously, but a lot of design work I know has been coming into designing the natural ventilation of this. This is a CFD analysis here that you can see. This work has been done very early on. It's one of the first things that they did. I think when at the competition stage they already had CFD analysis for the building. And the natural ventilation building is almost not used here because the customers, the people that are renting out the spaces of the Gherkin do not want natural ventilation. So in natural ventilation, again, another limitation is you have to make sure that the people you're designing the building for actually would agree to have natural ventilation, and they're okay with it. So it's very important. But in any case, I don't think that's such a drama, because the good thing is that there is still the flexibility for this building to be natural ventilated if it comes to that, which is a very positive thing. But in any case, I think it's majorly important to know who you're building for when you're designing your building. Otherwise, you end up doing a lot of work that nobody's going to really use. Another thing which I forgot to mention, sorry, the shape, the whole shape, the swirly shape here is actually being derived from the natural ventilation necessity. Because the air actually swirls around to the top. That's another of the... So I'll go a little bit through some software. I'm going quite a lot quicker than I expected, actually, so we're a little bit early on schedule. So I'll explain a little bit what dynamic thermal simulation is. Dynamic thermal simulation is used to not only design naturally ventilated buildings, it's also used to calculate the energy use of buildings. Most buildings now, most large-scale buildings in the UK are designed through with a dynamic thermal simulation. I think in the States it's also more and more the case, and many places around the world which are working in the starting or accept to be using this type of tools. Now what it is, it's a simulation that uses hourly climate data. So the climate information which I was mentioning earlier, including temperature, relative humidity information, wind direction, wind speeds, etc. are being, and also irradiation, solar irradiation, are being used. This information is hourly and is very detailed. Then the other type of information that's put into the software would be a 3D model of the building. So all walls, including windows, the actual form and shape of the building, and detail on the different construction details of all the different building elements are going to be also entered with their thermal properties. So you're going to have what type of walls you have, and all the properties of the different elements within the walls. It's the same for windows. You would have the window, of course, size, because you have a 3D model, and also what type of glazing you have, what is U value, etc. Then you're going to enter into the software what type of opening schedule you might have for the windows. So how much do they open and when in the year? It could be that one of the information that you enter in there is not going to be when your window opens, but actually depending on what it opens. So you could tell it if the temperature is over 25 degrees centigrade, then we open the window. Or if the amount of carbon dioxide inside the building is over a certain limit, then we open the window. Now, that means that if you have automatic controls, then it means that either you assume that people are going to open the windows when required, or you would have an automatic control, which is more and more the case now with natural ventilated, modern natural ventilated buildings. So you present these actions inside the building, and then the last thing that goes in there is the internal gain schedules. So how many people, how much heat, how much latent heat do they emit, and also the heat from lighting systems, from your computers, from anything that's inside the building. And the input, like any kind of software, actually any kind of exercise using software, what's most important is what you put into it. The calculation, the computer does it, but what the human does and what's important is what goes inside it. If you get that bit wrong, so for example, if your climate data is not right, then there's absolutely no point doing the exercise, because of course what you're going to get out of the software is going to be wrong, and so you're not going to have what you want. So I think this is the most important part of designing natural ventilated building with software, is this bit, and it's what normally when working with this tool is what's being the most checked. There's always double and triple check of what this information is. So what you get out of it, you get air temperatures. So you get also surface and resultant temperature, because of course the temperature that people feel is a result of the surface temperatures around them and the air temperature. We're not actually just feeling the air temperature. We feel what's called the resultant temperature. So you get all this temperature information on a hourly basis for the whole year. So you're going to get a variation of temperature all along the year. Then you get relative humidity and airflows, the amount of air, although you've got to be quite careful about using those. Predicted mean vote, so the comfort parameters maybe, to an extent. very importantly, you might get your energy use. Now, there's certain exercises that you might want to do if you're using the energy use. So maybe you will need to, for example, put a limit to the size of the boiler. So in the input section, which I was mentioning earlier, I didn't go through the mechanical systems, but that you can, in certain cases, depending on what you're doing, so also put some details about the mechanical systems or the building services system that you might have in your building. So if you do that, you can get a more accurate prediction of energy use. And peak energy demand. So what you're going to get? You're going to get the variation of cooling demand and heating demand all along the year for each hour of the year. And so if you have that, maybe you can decide what your peak is. I think it's you pick the maximum heating or cooling demand in your building. I think that's got to be used also very carefully because, of course, it depends on what input you have. And the input you have is supposedly a typical climate in your particular area. So your peak demand is not going to be the peak that's going to happen in the whole, it's not the peaks that you're supposed to design with. So you should design boilers and systems not with the peak energy demand from your software information, from your simulation, but with traditional means. I don't think software should be used for these purposes. But very importantly, if we're designing for natural ventilation, what you get is the resultant temperature for each hour. So you can get the frequency of occurrence, how much of a certain temperature we have during the year. So in the UK, we designed so that, for example, 28 degrees centigrade doesn't occur for more than 2% of the time. So you have certain guidelines like that that you may want to use. And if the temperature of 28 degrees happened for more than a certain percentage of the year, then it might mean that either you need bigger windows, so you can try to enlarge your windows, or it might mean that you cannot naturally ventilate and that the conditions are not good enough for you to be able to do that. Or alternatively, it might mean that in some times of the year you might want to air condition, so you might have a mixed mode ventilation system where you naturally ventilate it when you can, and the rest of the time you have an air conditioning system. Examples of applications are window sizing, like I was saying. It's very useful to do an analysis, so you can maybe do a variety of window sizes and try to decide what is the optimum size. So then you would need to have many runs of simulation. To evaluate the effectiveness of natural ventilation, to see the impact of thermal mass, I think is quite important. One of the questions that's very often asked, maybe if you have an office, is can I have a full ceiling in my office? And then you can, if you're using these tools, what you can do is you can put a full ceiling inside your building, simulate the building and see what the impact is and whether your building is still functioning the way you want it. The evaluation of energy use is a very important feature, of course, because then you can evaluate, this is one of the aim of the exercises. So if you have a mixed mode ventilation system, you can play with certain parameters and look at how much impact on overall energy use it has. Nowadays in the UK, we do the energy use evaluation as soon as concept design stage because it's required by planning. So to be able to go through planning, I mean, not everywhere in the UK, but definitely in London, London's mayor is requesting for us to be actually complying with certain energy efficiency limits, and so we have to carry out energy use simulation very, very early on in the design process. Now, what's really good about this is that to be able to comply to the limits of energy use, what you might need to have is naturally ventilated buildings. If you don't do that, if you don't evaluate the energy use early enough, then it might be that you end up with a building which cannot be naturally ventilated because its form doesn't allow you to do it. So very often is something that we have to do anyway. And of course, through these energy use simulations, it's possible also to compare the different energy efficient measures and what they do to your energy use. So the types of software, there's a variety. The ones which I'm familiar with and which are used the most in the UK and I think even in the States is TAS and IES. I think there's one of the sheets which you have, which you should have within your pack, which gives you details on some of the software with some quick explanations of what they do, what they are, and where you can find information about them. Both TAS and IES and any other software of this type, dynamic thermal simulation, which also is called dynamic thermal modeling, DTS or DTM, require extensive training. I don't think anyone could just go onto the software and use it straight away. I think it needs at least a couple of days, and then to be able to run the software and to be able to use it properly, I think it takes, may say, a month, 2 months experience to be able to really run with it. And I don't think it's a realistic thing to be deciding if you have a deadline on the design of a building for next month to be deciding to use that. I think it's something that it's important to prepare it and to take the time that's necessary to learn. Once it's learned, that's it. Once one software is learned, the good thing is because they all function according to the same principles, then you end up being able quite quickly to use the other software and design with them. But I don't think it's something that should be done in a rush. It takes a while to learn. So just the little picture on the left here, this is not pictures from my own designs, and this is just a completely different building. But this is showing the kind of detail that you get in the 3D simulation of the building. So if you look, you have some details of the facade, etc. This, I suspect, will be some information. I suspect that this is going to be the variation of temperature during the year. Maybe the red bit could be the heating system, for example. I think so. So if you, this is the kind of graphs that you get out of your software, and then from that you might decide, I'm going to look at how the frequency of occurrence of certain temperatures. So you get graphs like that tell you I have a certain number of hours during which the temperature is over my limit. As a health warning, like I was saying, it's very important that people that use this are trained properly. For us, I've had people from in my previous job, I had a team of engineers doing that kind of work, and because there was enough people to be employing somebody to train us specifically, we had people coming straight from the software providers coming and training us, and they do that. It's quite expensive, but it's definitely worth it. It makes things a lot quicker in the long run, and it makes it a lot more accurate and precise. It's important to be reviewing because there's so much information that goes into these machines. There's so much detailed, very, very detailed information. What actually takes a very long time is not putting the stuff into the machine and running the simulation. What takes a long time is to make sure that what goes inside the machine is right, and that there's no errors, because the machine is not going to make mistakes, but people that put the information into it do make mistakes all the time. And even extremely experienced building physicists, the building physicists are the people doing that type of work, extremely experienced building physicists make mistakes all the time. So the review regime is the most important bit, and the review regime of all the input is the most important bit. So there can be very formalized way to do that, where we have sort of forms to fill in and people tick in what has been reviewed and hasn't been reviewed, but it has to be done extremely carefully and thoroughly. Otherwise, there's big problems. Another thing is when a simulation is carried out, very often it's very important to be carrying out the simulation for the purpose of what you want to do. So the simulation to evaluate the energy use of the building should, in theory, be completely separate to the simulation to do natural ventilation. Why? Maybe because if you do natural ventilation, what you want is you want to design for a worst case scenario. So if maybe you're going to use a climate file, which is a very hot summer year. And that particular climate file might not be the climate file that you want to do your energy evaluation. Your energy evaluation will need to be using a climate file which is an average year. The other reason is because very often you might change the parameters of design. So maybe for worst case scenarios for natural ventilation, you might want to put more people inside the building, or you want to put more computers just to understand what the worst case scenario is. And the last thing that might happen is that sometimes these softwares are not perfect, and sometimes they contradict. They go into a kind of loop. What happens is that if you have a rule that says open the window when it's 20 degrees. What might happen, you open the window, so software opens the windows, it gets cooler inside, and maybe it gets cooler, maybe if the air outside is 15, say, because it's a very bad summer in London, then it's 15 inside, and maybe you have another rule inside the software that goes, well, actually put the heating on when it's less than 15 degrees, and you get a kind of opening window, closing, opening heating system thing going on inside your software, which doesn't really work really well. And you have really high heating demand and windows that open and close all the time, which is not realistic. So very often it's a good idea to be simulating summer and winter separately, depending on what you're doing. It's not always the case, but I think it's possible to try to do that. And my last health warning, I've been insisting a lot on it, but it's only as good as what you put in. What the software does is what people tell it to do, not it doesn't work on its own. So it's like any, it's like hand calculation are the same. They're only as good as what you give them. But computer simulations don't get any better than the person that's designing with them. Computational fluid dynamics software is the other type of tool which I have been mentioning. I had some more pictures. I don't know where they're gone. It doesn't matter. Oops. Sorry. So computational fluid dynamics simulates air movements and air temperatures inside the building for one state. So it's not dynamic. We're not looking at whole year. We're just looking at one single moment in time. So it's steady state, basically. So the types of applications, the thing is you're not going to look at comfort parameters or whole year. You're just looking, so you take certain assumptions. You might have a certain amount of pressure on your building, certain conditions of the air is at a certain temperature, the surfaces inside your room are at a certain temperature, so you have to know to have that as assumptions in the first place. And what it's used to do, it's used to evaluate the pressure losses. It's used to evaluate the drafts, how much air goes inside at a certain time. So if you have a cold air movement inside the room, or you can do that both for air conditioning and natural ventilation. It's used for air conditioning systems, which in some cases for very large rooms, for example. It can be used to look at the wind pressure, also the wind speeds around the building. So not just on the building, the pressure on the building, but also around the building. If you want to evaluate the comfort of the pedestrians around buildings, so that people don't fly off and stuff like that. It sounds silly, but it is something which is necessary in some areas, if you have very high buildings in particular. And And the type of software that I've only got a few there, they're called CFX, Fluent, CD Star. The one I know is CFX. They all are extremely complex software to be handling. The people that tend to use computational fluid dynamics, that's what they do. That's their job. They do that for years. The thing is that it's so involved in terms of knowledge and or knowledge of the science of fluid dynamics and knowledge of handling the software that it's very difficult to be doing that and working on other aspects of the design of the building. So very often you will have a CFD analyst person that would be either somebody that is employed separately to the normal design team. So very often this is subcontracted as an exercise because it takes so much time and so much involvement in doing it. And personally, I've rarely needed it. I've needed it in very few occasions. And so it's kind of, it's a lot better to do that externally for safety, because it's so involved and intense as an exercise. The other thing is, I mean, I shouldn't say, but really, I've had somebody doing this type of work actually in my team last year, and he got. It was interesting because he spent about six months just doing CFD analysis, and it's very intense. You're in front of your computer, and the thing is that because he had to learn the software whilst doing the work. It took quite a lot longer than we thought it should take, and eventually it cost us a lot more money than it would have if we had done it externally. It was really interesting for the guy that was doing it because he was learning a new skill, obviously. But I think if it's something that's done in a commercial environment as an exercise, not in a research environment, then there's always time and cost limitations. And because it's such a specialist area, it's better to give it to the specialist that actually can do it and do only that. So that's just an opinion. Not everybody thinks the same. These are examples of pictures. The two at the top, which you've seen already. I haven't put any of the work which I've done for copyright reasons that we've done in my team. But this is a window simulation, so where you can see the flow of air just going through here with the different temperatures being represented by the colors here. Here, this is, I believe, an example of classrooms where you can see all the red bits here are people. So you can see the air plummeting on the top of the people and being hotter. This is sort of the cut taken through an office building, which I believe has some form of displacement ventilation. So the air is coming from the bottom and heats up progressively towards the top. They're very useful study. It's very different to what I was talking about earlier, dynamic thermal simulation, because it only takes one single time. It just looks at one time. The problem is that very often you need to look at many times, and so you need to do loads and loads of these simulations to be able to understand what's going on. So this is the kind of stuff that comes out of this software. Like you can see, it's kind of quite useful. Here we have wind speeds, so this is not temperatures, these are wind speeds. So you can see the effect I was talking about earlier, about the fact that the wind is higher on the top than it is at the bottom. It's quite obvious. And then you can see the air coming inside, and maybe there's a bit of a draft here. It's kind of useful to be understanding drafts. And if you want to put a wind turbine in a building, you can see that the plume comes at this point, and that maybe you want your wind turbine to be higher than that. So it's kind of, it's very useful work, extremely time-consuming. It's about the most time-consuming type of simulation exercise that I've come across. The health warnings I have for this software, training is indispensable. I won't stress it enough. I've been trained, I can't do it. I've been trained for days on days on this software, I can't do it. And because this is not just about the training itself, this is about the training and the learning phase after that, that takes months and months. So the review is even more important. The problem with the review with using CFD is that it's kind of difficult to find reviewers that understand CFD as well as the guys that's doing the simulation. So it's another reason why I often would prefer subcontracting something like that, because it's safer. Steady state, it just does one particular state in time. It's very, very specialist. There's problems of accuracy. The softwares perform very differently in terms of accuracy, and it's kind of, I think it has to be considered as a very approximate simulation type, because winds are a very difficult thing to be simulating. The equations that govern them are extremely complex, and I think it's actually quite recognized that still today these softwares kind of give an approximation of what the wind does. It's not a very accurate simulation. It's very time intensive, and I think it's important to understand the boundaries of the simulation. So for example, there's no point designing just having one building with nothing around it and decide that it's natural ventilated, get air to come inside and not understand what goes around this particular building, because the wind is affected by buildings around the building that you're studying. So you need to extend the boundaries of your study, not just to your building, but to what's around it. And in a way, there's a little bit of a contradiction in that the buildings that are around your building might change. And so it's not just about deciding what the boundaries are and what are the buildings around your building, but it's also about making sure that the potential for other buildings around your buildings to change. So that has to be taken into account whilst looking at this type of exercise. Is there any questions? I'm a little bit early, but no, not so early. I've got about 10 minutes for questions, if there's any question. No? Okay, well, that was the first part. I think we had 10 more minutes before a break, but if there's no question, I'm sure we can take the break now. Yeah? Okay.